Last video, we started discussing the Zeeman effect, right? This Zeeman effect was essentially an effect due to an externally applied magnetic field on our hydrogen atom, and we showed that the Hamiltonian for that interaction was just the Bohr magneton times the strength of the magnetic field over h bar times the gyroscopic ratio associated with the orbital angular momentum times the LZ operator and the gyroscopic ratio of the associated with the electron and the spin angular momentum operator in the z direction. And we stopped there and essentially said, okay, now we have to apply this Hamiltonian as a perturbation to our hydrogen atom. But we pointed out that, typically our hydrogen atom uh, wave functions, our unperturbed wave functions, are those NLM, radial and spherical harmonic wave functions. But when we're applying this Hamiltonian, we have to also consider the other perturbations to the Hamiltonian we've looked at. In particular, we looked at this fine structure perturbation previously that involved that relativistic correction and the spin orbit interaction correction. And we want to consider both of these terms when we're trying to determine what the spectrum of our hydrogen atom is going to be and what those states are going to be. So how can we consider both of these? Well, we're going to use perturbation theory and we're just going to apply both of them, but we have to do that individually, right? So, if you think of the whole system Hamiltonian for that hydrogen atom, it's going to be the just zeroth order hydrogen atom, one that we solved that gave us these NLM wave functions, plus those two, the Zeeman perturbation and the fine structure perturbation. So we're going to take a zeroth order perturbation, apply one of these perturbations. That's going to shift our energy levels and possibly modify our NLM degenerate states, maybe lift the degeneracies in that. And then we're going to take whatever the result of that perturbation is as our zeroth order Hamiltonian and apply the second perturbation. But the question still remains, well, which perturbation do we apply first? And to answer that, it basically boils down to, which one's stronger, right? We treat perturbations as smaller modifications to a large zeroth order energy. We want to apply whichever one's larger first. And that's going to depend on essentially the strength of the magnetic field. If we look at the energy shifts when we applied that fine structure perturbation, we saw that they sort of shift the energy levels from 0.5 gigahertz up to about 43 gigahertz, and we saw sort of the level of those splits. Those are give us the energy scale of this fine structure perturbation. The Zeeman energy, well, depending on the strength of that magnetic field, if we apply a really large magnetic field, these energies, these terms in that Hamiltonian are going to be larger than all of those shifts, and we'll want to apply it first. If this magnetic field is small, those shifts are going to be smaller, and treating it as a perturbation to these perturbed states is still valid. So that's what we're going to do next. Today, we're going to look at the low field case in this field, in this perturbation where the magnetic field applied is relatively weak, and we will apply it as a perturbation to our zeroth order Hamiltonian, which is going to already include that fine structure perturbation we previously looked at. So let's do that, right? We have, so once if you recall, once we applied that fine structure perturbation to it, we saw that coupled our states, right? It had that spin orbit term that coupled the spin and orbital angular momentum. So we ended up with the states afterwards were the NLS JMJ states, were the eigenbases for that perturbed Hamiltonian. Now, some of these states were still degenerate. If we looked up here, there were still degeneracies in those perturbed states of the fine structure after applying that fine structure perturbation. So we're going to have to use these states to apply our degenerate perturbation theory with our Zeeman perturbation. Remember, degenerate perturbation theory is essentially you're supposed to diagonalize the perturbation Hamiltonian in the degenerate subspace. So we have to write our Zeeman perturbation in that perturbed or zeroth order in terms of that zeroth order bases, and then diagonalize the degenerate subspace of that matrix. So our challenge now is can we write this Hamiltonian or these matrix elements in this basis? And one of the things we're going to notice is the perturbation Hamiltonian, or I'll just rewrite it here. This Zeeman perturbation is mu b over h bar. It depends on that L sub z operator and that S sub z operator. So these are diagonal in the uncoupled bases, not the coupled bases, right? They're individual angular momentum, one associated with the orbit, one associated with the spin. So we don't really know. We would have to do a lot of work to figure out what these are by just brute force calculations. But we can use our Clebsch-Gordon coefficients to kind of switch this over, right? This matrix element here can, we know that NLS JMJ, that state, that basis state can be written as a linear combination of the ML and the MS terms, where this is going to have those Clebsch-Gordon coefficients, C, M1, M2, M, J1, J2, J, that we could look up from our Clebsch-Gordon tables on that N, L, S, M, S, M, L, angular momentum basis state. So we can write this as a linear combination that and use our Clebsch-Gordon coefficients and just look them up from the tables to determine what these matrix elements are, right? When we do this, essentially what we're getting at is this NL SJMJ H sub Z prime NL SJMJ matrix element can be written as subbing this for the ket side and then the corresponding bra for the bra side as sum over MS those Clebsch-Gordon coefficients NLS MS ML and then those Clebsch-Gordon coefficients are just those projections of the NL S J M J M S. Oops, got ahead of myself. It's the projection of those coupled states, NL S J M J, onto the uncoupled basis states, is what those are, and then operate that Hamiltonian on that times the same thing on the other side, MS, MJ, those Clebsch-Gordon coefficients, NL, S, MJ, MS, and it's an NL, S, J, MJ times the NL, S, MJ, MS. So again, all we've done here is we're changing bases of this Hamiltonian to one because we know how these, let me highlight these, we know these operators are, these uncoupled states are eigenvectors for these operators, so we're converting these coupled states into the uncoupled bases by using these Clebsch-Gordon coefficients. And we're doing that on both sides. And that's essentially the gist of what we're doing. That'll give us our matrix element that we're looking at in the zeroth order bases and allow us to diagonalize it see where the degenerate subspace is, and proceed with degenerate perturbation theory. So let's just look at a quick example, because I know that's kind of a lot to take in. Let's look at the n equals 2, L equals 1, S equals 1/2 state in hydrogen. Now this, if you remember, J can have possible values, all possible values from L plus S all the way down to the absolute value, or the difference between those two possible values. So in this case, we have J is equal to 3/2 and J is equal to 1/2. And then the MJs can go between those. So they can go from -3/2, -1/2, 1/2, and 3/2 if we're in the J equals 3/2 state, and or for the MJ for the 1/2 total angular momentum, it can just be -1/2 or 1/2, right? So our basis states, there are essentially 6 of them. Those states, there's these 4 and these 4. Now, if we want to look at, just refreshing our memory on the Clebsch-Gordan coefficients, that NLS J, I'm just going to write it as JMJ. So if we were to look at the 3/2, 1/2 JMJ state, and we want to convert that to the uncoupled bases, well, we're going to have to look it up in a Clebsch-Gordan table. If we look at the corresponding J equals 1 and 1/2 table, because remember, we're adding this angular momentum equal to 1 and the spin angular momentum equal to 1/2. If we look at that table, and in the JM bases, we're at 3/2 and 1/2, we get that in the uncoupled bases, it's 1/√2 in the ML equal to 1, MS equal to -1/2, and the √2/3 times that uncoupled basis term. So we can write this vector, or this basis vector, as 1/√3 times the NL, so it's going to be the 1 times 1/2 is the L. This is, again, just to write these, to be clear about those things, this is LS, MS, MJ is the quantum numbers order that I'm writing this basis in. So it's going to be the 1, 1/2, and then 1, -1/2 term, plus √2/3 times the 1, 1/2, -1, oh, sorry, not -1/2, that would be silly, 0, 1/2 state, right? So we've got that coupled basis term written in terms of our uncoupled bases written here. Similarly, if I wanted to look at, say, the 1/2, 1/2 coupled basis vector, that's going to be, well, if we look over here, we just take, this 1/2, 1/2 column here, and we get these two coefficients for these two basis vector states. This becomes 2/3 square rooted times 1, 1/2, 1, -1/2, and this is going to be minus 1/3 all square rooted 1, 1/2, 0, 1/2. And now I've got that coupled basis vector in those terms. So now I can, using my Clebsch-Gordan coefficients, I've got the coupled bases written in terms of the uncoupled bases, and now I can, apply, if I want to, I can take that Zeeman perturbation, operate on this, but because I know how that H sub Z Hamiltonian, which again is proportional to the Z components of the individual angular momentum, I can figure out what this the action of this perturbation is on this vector because I've been able to write it in terms of eigenvectors for that operator. So really quick, essentially, if I want to do that for this 1/2 state, say I just the 1/2 in the coupled bases again, operating on just L sub z, that matrix element is going to be, well, I know that 1/2 element is going to be 2/3 square rooted 1 1/2 1 negative 1/2 plus minus 1/3 square rooted 1 1/2 0 1/2, operating on L sub z, and then the same, the corresponding ket on the other side, 1 1/2 1 negative 1/2 minus 1/3 1 1/2 0 1/2. And because I know how LZ operates on these two vectors, because they're eigenvectors, LZ, just to refresh our memory, LZ operating on LS ML MS just gives me ML times H bar times the same state. So it's going to bring out a 1 for this one and a 0 for this one. So when we operate on this, and then because it gives us the same vector, we're just going to get, due to orthonormality, this term's going to be collected. These two are going to remain, and then these two are going to remain. And what we end up with is just 2/3, root 2/3 times H bar minus root 2/3 times 0 H bar. So that term goes to 0, and we know that that matrix element, the LZ operator in the coupled bases, has a matrix element there that is root 2/3 times H bar. So we can do this, and we can sort it out for all the different matrix elements of our in our coupled bases. And when we do that, this is going to take a while to write here, but bear with me. L sub z, that operator, is going to be written as H bar. I'll speed this up. Where I've written, the basis vectors in this JMJ eigenbases are 3/2, 3/2, 3/2, 1/2, 3/2, negative 1/2, 3/2, negative 3/2, and then the 1/2, 1/2, and negative 1/2, 1/2 basis vectors. Similarly, the S in the same basis operator, the S sub z, is equal to H bar. Let me try to write this one and speed it up. Where again, this is in the same basis, so it's the same order of basis vectors we have there. But now that we have our L sub z and our L sub s operators, our Zeeman Hamiltonian is just that mu b over H bar GL L sub z plus GE L sub s. S sub z. We have our Zeeman Hamiltonian written in the 0th order bases, and we can identify degenerate subspaces and diagonalize those, right? And when we do this, we're actually kind of fortunate here. We can look at this if we go way back up here to our identifying what our you know degeneracies are. Our degeneracies are based on the total angular momentum of these things. So if we look at the degenerate subspaces where J is equal to 3/2, and that what we're seeing is these top four sort of rows, which would correspond also to these first four columns, in that degenerate subspace, which is that J equals 3/2 subspace, this matrix and also this one. So when we add them together, they will still be diagonal. They're both diagonal. So we've kind of lucked out that in this 3/2 degenerate subspace, our perturbation matrix is actually diagonal. Similarly, if we look at this J equals 1/2, oops, I just realized I wrote this wrong. This should be -1/2 here, and this is still just the J 1/2. Sorry about that. This degenerate subspace with the total J being 1/2 is also diagonal. So in both degenerate subspaces, our perturbation Hamiltonian is going to be diagonal. So we just have to sort of figure out what these are, add these two matrices together with the appropriate sort of scalar multiples, and we know what our energy shifts are going to be, right? So if we look at focusing just on this 3/2 degenerate subspace at the top, what we end up with is adding those together. Our perturbation Hamiltonian for the Zeeman term is going to be mu b b times this 4x4 matrix, and when we add those together, taking into account that our GL, if you recall, G sub L is just 1 and G sub E is equal to 2. So plugging that value in for here, and then using these two matrices that we just figured out there and add it together, we get to 0, 0, 0, 0, 2 over 3, 0, 0, 0, 0, -2 over 3, 0, and then -2 on the bottom, right? So we see that in that 3/2, J equals 3/2 degenerate subspace, our perturbation, our Zeeman Hamiltonian is diagonal. So we know, we don't have to do any work to diagonalize it. We got lucky. It's already diagonal. We know that those states, those 2, 1, 1/2, 3/2, 3/2 states, where this is, the N, L, S, J, M, J bases. We know those four states in that degenerate subspace, which, those four states are just 2, 1, 1/2, 3/2, 1/2, and then the next one's the only difference is going to be the -1/2, the -3/2. Those states stay the same. The perturbed states are the same as the unperturbed states. But the energy shifts, we can just pull off from the diagonal terms in that Hamiltonian are going to be 2 times mu b b. This one's going to be 2/3 mu b times b. This one's -2/3 mu b times b. And this last one's -2 mu b times b. So what we see is these four states that were still degenerate after we applied that fine structure perturbation. We had all of those states were at some energy level after applying the fine structure. If we were to sort of plot those energies as a function of applied magnetic field, they get split off. One goes up and one goes down at -2 mu b and 2 mu b, and then two others kind of go split like that as well at 2/3 mu b and -2/3 mu b. And we could also look, do the same sort of thing and look at the other degenerate subspace, this j equal to 1/2 subspace. I'm probably going to assign that to you as a homework problem, and we'll see they split as well. Now, we were looking at a specific example, given L equals 1 and J, L equals 1 and J, S equals 1/2 states. There's a theorem called the Wigner-Eckert theorem that is, we're not going to derive it. The book doesn't go through it. It involves essentially a lot of tensor math, but basically allows you to generalize this Zeeman effect to sort of any J and MJ states that you're concerned with. To sort of see how it works, right? Consider, we've been looking at these these two p states. Consider the z projection of the total angular momentum for that operator for the two p subspace, right? This is going to be equal to h bar 3/2 0 0 0 0 0 0. I'll speed this up. Right. So this is that same L equals 1, uh, S equals 1/2 uh, system, and this is the JZ operator acting on those states where we have, in the J MJ bases, we have 3/2, 3/2. This is the 1/2, positive 1/2, negative 1/2, negative 3/2, and then the 1/2, 1/2, negative 1/2 sort of subspace here. This is the JZ operator, it's diagonal. We can sort of just by inspection compare this with the LZ operator, say, that we wrote in that same bases. And if we look at the degenerate subspaces, if we look at that J equals 3/2 subspace and that J equals 1/2 subspace, what we can realize is that these two matrices in those subspaces are proportional to each other. So what we have is these J, MJ, LZ states J, MJ prime. So all the matrix elements, different MJs in that subspace, are equal to the J, MJ states, the JZ matrix elements times some proportionality constant, some proportionality constant that relates the matrix elements in the subspace of our LZ operator to our JZ operator. And it turns out that that proportionality constant comes from this Wigner-Eckert theorem. And what we can see, what essentially that says, is that CJM is equal to JMJ. It's going to be L dot J JMJ over H bar squared J J plus 1. Sorry, put that bracket in the wrong place. And this is the projection theorem, which is an example of the Wigner-Eckert theorem. They call it, it's the projection theorem because oops, that wasn't supposed to be an eraser, because it depends on the projection of the J operator onto the L operator, or whatever operator we're trying to write. In more generally, or written more completely, what the Wigner-Eckert theorem essentially says, or can be written out as JMJ of the Z component of some vector operator, JMJ J prime. Those matrix elements can be written as J, M, J, that whatever that vector operator is dotted with that total angular momentum operator, J, M, J, uh, over H bar squared J, J plus 1 times J, M, J, J sub Z, J, M, J prime. This is sort of the full form of that Wigner-Eckert theorem, and there's a lot in here. But basically, in our case, we were looking at L, so we were looking at the Z component of the L vector operator. But that Z component is going to be proportional. That matrix element is going to be proportional to the Z component of the J total angular momentum operator, and that proportionality constant is the projection of the diagonal projection. So again, the primes aren't typos. The diagonal element of the projection of the total angular momentum operator on that vector operator we're talking about. In this case, it was our angular momentum. And so that's what we can use to sort of generalize the Zeeman effect. To apply this, so in going back to the case we're looking at, our v dot j for our orbital angular momentum is an L dot j operator, and we need to figure out what that is, right? Since j is equal to L plus s, our total angular momentum in this case is that, s is equal to j minus L, s squared is equal to j minus L squared, which is equal to j squared plus L squared minus 2j dot L. This means that j dot L is just equal to 1/2 bracket j squared plus L squared minus S squared. So we can sort of use this identity, plug it in to this matrix element up there, and what we get is this J M J L dot J J M J term, because these are eigenvectors for every one of these operators in that J dot L. This term ends up just being J M J. I'll just write it out, 1/2 J squared plus L squared minus S squared J M J. And knowing the action of those operators on those eigenvectors, this ends up being J M J. This is going to be H bar squared J plus 1 plus L plus 1 minus S plus 1 J M J. So taking all that and applying it using that Wigner-Eckert theorem, that means our J M J L Z J M J prime matrix element, our LZ operator written in that term, is 1/2 H bar squared. Let me just bracket this out. H bar squared J plus 1 plus L plus 1 minus S plus 1 all over top of H bar squared J plus 1 times J M J J Z J M J prime. If we take our the case we were looking at, that J equals 3/2, L equals 1, and S equals 1/2 case we were sort of looking at, this all reduces to essentially 2/3, right? So this ends up being the J, M, J, L, Z, J, M, J prime is equal to 2/3 J, M, J, J, Z, J, M, J prime term, which, if we go all the way back up and look at what our JZ operator was in that degenerate subspace, and all the way up here to what our LZ operator was in that degenerate subspace, we see that that's the proportionality that sort of relates those two by comparison. So um, we can sort of use this, we've sort of generalized this result of how to write the LZ operator in terms of a JZ operator for any J and MJ values. We can do the same thing for the S sub Z operator. And we can use that to see what our energy shifts due to that Zeeman term are, right? Those energy shifts are just the diagonal, you diagonalize the perturbation in the degenerate subspace, so that NLS, J, MJ, those matrix elements are going to be, we can use these sort of generalized, well, not that generalized result, the actual generalized results that we got to sort that out. And when we do that, well, these matrix elements are J, M, J. Well, it's just not G. Mu B, that Zeeman Hamiltonian is mu B B over H bar times G L L sub Z plus G E S sub Z and L S J M J. When we plug that in, we use those generalized results to get these matrices. And what those generalized results end up looking like are mu B times B over H bar times G sub L all times J plus 1 plus L plus 1 minus S plus 1 over 2 J plus 1. And then this term over here is just G sub B. Very similar, J plus 1 plus S plus 1 minus L plus 1 over 2 J plus 1 times that matrix element of the J, MJ, I forgot the S, that JZ operator, sorry, got a little tongue-tied there, MJ. Right, this matrix element here, well, JZ is, these are eigenvectors of that JZ operator. It's just going to be NLSJMJ times MJH bar NLSJMJ, right? Which is just, this is just a scalar, it can come out, and those are normal, so this is just MJH bar. So this entire first order, these energy corrections to that thing can just be written as mu B B H bar times, I'm not going to rewrite the whole thing, but that bracketed term in there times MJ H bar. The H bars cancel. And what we can do is we can, cancel those H bars. This whole term here, we can just define as some constant. Given some J, L, and S values, this is going to be what we call the Landé G factor. And it is equal to, GL, J plus 1 plus L plus 1 minus S plus 1 all over 2J plus 1 plus GE J plus 1 plus S, S plus 1, minus L, L plus 1, all over 2J, J plus 1. And we call this the Landé G factor, and that means we can write our Zeeman perturbation or Zeeman energy corrections in this low field limit as just mu b times that Landé G factor times the quantum node, that sort of Z projection of our total angular momentum quantum number. That's a really nice simple result. You turn up the magnetic field, you're going to see these sort of linear shifts in those energies, and those degenerate levels are going to split in that way. For if that 2p state case we're looking at, we can determine that G sub j for the 3/2. For the j equals 3/2 case, when we plug in all those j, l, and s numbers, this ends up being 4/3. The g for the 1/2 total angular momentum subspace, that Landé G factor ends up being 2/3. And we can figure out those splits. In general, this for what we've been looking at, we have our J for S equals 1/2. We're looking at the hydrogen atom with the electron. Our J is going to be equal to L is equal to plus or minus that 1/2, or J is equal to L plus or minus that 1/2. If we plug that into it, that Landé G factor can be reduced to 1 plus or minus 1 over 2L plus 1, where the plus or minus relates to which J state we have. And when we get that, if we plug that into what our energy correction is, we end up with the energy correction for the Zeeman energy correction in our hydrogen atom is mu b times b mj 1 plus or minus 1 over 2L plus 1. And this is a nice generalized result that works for any, knowing the angular momentum states that we're looking at, those degenerate states, we can see what those shifts are going to be. So if we were to plot the energy as a function of magnetic field of some of those states, let's say we look at that 2p 3/2 state there, we're going to have that's those J equals 3/2 states. We're going to see them split like that, like we had derived, brute force. But this, given the different L states and MJ states that are degenerate there, we see those splittings, and the 2p 1/2 states are going to split accordingly, following the same thing as well. We get splits like this. But anyway, so we've derived that general result. There's a lot to get there. We're going to discuss this more in synchronous sessions. I'm sure there'll be questions. Recapping, taking a step back, getting out of the thick of it. What we've done is essentially we're looking at our hydrogen atom. We're taking into account both the fine structure, those internal perturbations, as well as this Zeeman perturbation due to an external field. But when we look at the low field case, we take the perturbation from the fine structure, the result of that, as our 0th order Hamiltonian, and then apply the Zeeman term as another perturbation to those states. And when we do that, we saw in that low field case, we saw that those Zeeman states remove the degeneracies that remained after the fine structure was perturbation, and it does so with energy shifts described by that. If you have questions, email me. We'll discuss this more in our synchronous sessions. I will see you then.